So this example, let us consider a solid feed of 26.4 kg per minute at 95 degrees centigrade and 1 bar pressure, the conditions given, containing calcium carbonate powder and magnesium carbonate powder, they are at 50-50 weight ratio, and water at 6.6 kg per minute at the same temperature and pressure are fed in a continuous classifier. So the water information has been given, that is the fluid, and calcium carbonate and magnesium carbonate powders, they are put into the classifier. The powder has particle size distribution between 1 to 10 millimeter with geometric mesh type of discretization 1. It has been fixed, PSD, and weight fraction of PSD intervals are 0, 0, 0, 0, 0, 0.2, 0.2, 0.4 and 0.2. So this entire, if you add it up, then you'll get 1. So basically we have to add this information to know what is the percentage of particles in a particular size range. So this means that there is probably no particles between 1 to 5 or 1 to 6 millimeter range. All the particles are from 6 to 10 millimeter range, and they fall over here. Anyway, we'll see it later. And then sort particles into different fractions by their particle cut size of 8.5 millimeter, separation shortness of 0.9, and fluid load of fines outlet 2. Use Roger classification, and there is no change in flash condition. Now clearly we are not using air flow rate over here, so this is not a sifter, this is a elutriation. Okay, so this is the first problem. Then the second problem, it says the above problem has to be repeated by particle density. Okay, so here we are using particle cut size, but here we have to use particle density and fraction 0.25 of fluid in the feed to fines outlet. So here we are using load, here we have to use fraction, and classification function also has been changed from Rogers to Plitt. And the third problem is repeat the above by particle settling velocity of 3 meter per second. So these are the three problems and we'll solve, and then we'll go to the next page. The first problem in this page is repeat above by using tabular data of particle size. So here the particle size and grade efficiencies have been given. Okay, and the fluidizing gas of 170 kg per minute at 200 degrees centigrade and 1 bar containing 99.8 weight percent of air and 0.02 weight percent of water is also fed into the classifier. Obviously, this is a Sifter model problem. Then repeat the above by using gravity counter. This is a Sifter model with cut size and cut density as before, and a vapor stream pressure drop of 0.1 bar. So it is not using the delta P equation, rather it is giving the pressure drop information up front. And then repeat the above by using gravity cross current shifter model with shifter length 3.5 meter and width 1.5 meter. And finally, repeat the above using impeller wheel shimple shifter model with separation efficiency of 90%, impeller radius and height have been given. Okay, so let us solve this problem. So let us go to the first page. So for that, first go to properties and we use calcium carbonate, magnesium carbonate, water and air. But here calcium carbonate and magnesium carbonate will be solid, right? So you use solid over here, solid, and then press next, and method, let us use solid, run. But if the flash condition has to be checked, then we have to use some other property methods also. So let us use ideal property method. So if we choose ideal and run, then vapor liquid equilibrium calculation also can be done. Okay. So basically we have used two selected methods, one ideal, one solids. Now go to simulation. Now first let us go to the setup, solids and PSD. So solid, because the feed is having some particle size distribution. And what is that? The particle size distribution between 1 to 10 millimeter with geometric mesh type of discretization 1. So this information you have to provide over there. So here it is geometric mesh type with discretization 1 between 1 to 10 millimeter and create PSD mesh. So we have the intervals 1, 2, 3, 4 up to 10 between the lower range and upper range. And if we remember, we have 10 intervals over here, and the weight fractions of the 10 intervals are 0, 0, 0, 0, 0, 0. So first 6 zeros and 0.2, 0.2, 0.4, 0.2. So there are 10 intervals. And those 10 intervals we have to put while we set the particle size distribution. First 6 will come as 0. This will be 0.2, this is 0.2, this is 0.4, and this is again 0.2. So that's how the intervals will be set. Let us go to the stream, and we have to set the feed, right? So let us choose feed over here, feed input. So the mixed input, we have only water, right? Let us read the problem once again. Solid feed is 26.4, 95 degree centigrade 1 bar with 50-50 weight percent calcium carbonate and magnesium carbonate. While water is at 6.6 kg per minute at the same temperature and pressure. So water will also be 95 and 1 bar. So it is 6.6 and that is 26.4. Let us write 95 degree centigrade, 1 bar, and mass flow of 6.6. That is liquid, mixed flow. We have missed the specification of Cl solid. So we have to go back to the stream class, and global, we have to choose this one, that is mixed Cl solid with PSD, so that the Cl solid portion is activated. Now again here we have to place 95, 1 bar, mass flow rate of 26.4. It is kg per minute, right? This is kg per minute. So here also we have to place kg per minute. We can check once more. Yeah, this is kg per minute, right? And 50-50. So this one is mass fraction. This is 0.5 and this is 0.5 as well. Now we have to set the particle size distribution. So weight fraction has to be given over here. Okay. So we write 0, 0, 0, 0, 0, 0, 0.2, 0.2, 0.4 and 0.2. So this is how the weight fraction has been defined as per the problem. So the feed material specification is complete. Now go to the classify input. So the first one, we have to use classification function. Sifter model will come later. So use classification function. And what are the other details? We have to use particle cut size of 8.5 millimeter, separation sharpness 0.9, fluid load of fines outlet 2, Rogers, and there is no change in flash condition, right? So this information we have to give. So let us remember this information and go back to our Aspen Plus window. So particle cut size 8.5 millimeter, separation sharpness 0.9, right? And then it is load, separation sharpness 0.9, fluid load of fines outlet 2. So we have to find the fines load of 2. And lastly, there is no change in flash condition. So if there is no change in flash condition, that means the change in pressure is 0, change in temperature is 0. So we do not have to put anything over there. In short, our specification is complete. Now run it. So we find a problem over here. The results are available, but they are with warning. Let us see what is the warning. So we check status and we find the following unit operation blocks are completed with warning. And it says that specified fluid load of fines 2 kg is too large over here. So maximum possible load, whatever Aspen has found out, that is 0.304 to be very specific. So let us take a lower value. So let us take not 2, we will take 0.2 and perform the calculation once again. So for that, we will go back to the specification and instead of fluid load 2, we will put 0.2 and run it once again. So once we run it, now the results are available without any issue. Let us see the stream results. Let us see the fluid load first because that is the problem it was showing. Now check the mass flow. Here you can see what is the mass flow rate of water, because water is the only fluid over here in the fines, that is 260.948. Okay. And what is the total solid flow in the fines? Combination of them, that is 652.371 multiplied by 2, magnesium carbonate and calcium carbonate. So if you find the ratio between them, that is this by this, you will find 0.2. Okay. Now let us check the other results. For that, we go to the CL-PSD stream. If we open it, at the bottom, we find PSD. So this is the fine stream and this is the quartz stream. You can see in the quartz stream, almost nothing is there between 5 to 6.3. All these particles of this size has come to the fine stream. And the quartz stream, maximum amount of particles are there from 8 to 10 millimeter range. So that is only around 87%. Whereas only 5.5% of the particles in 8 to 10 size range group has come to the fines. So we can say that this classification function has comfortably separated the fines and quartz particles with this calculation. Now go back to the problem statement once again to check the next function. This is the use split function and particle cut density of 3 grams per cc. But here we are using 0.25 of fluid in the feed to fines. So we are not using load over here. We are using the fraction of 0.25 fluid in the feed to fines. Okay. So let us go back. Use split function and particle cut density. For that, go back to classify input. This is split function and we use the particle density and 3 grams per cc, right? And instead of load, we use the fines fraction, and that fraction is 0.25. All others are as before. And let us run it. Okay, now results are available. Now here you see in the fines, what is the amount of water? This is 99. And in the feed, what is the amount of water? It is 296 or 396. So 99 by 396, a simple calculation will tell you this is 0.25. Okay, that's exactly we have used. We have used over here 0.25 fraction fluid in the feed to fines outlet. And the same thing has been said over here. And finally, repeat the above by particle settling velocity of 3 meter per second. So for that, let us go to the particle settling velocity and let us use 3 meters per second and check how it performs. Let us go to the particle size distribution. Yeah, so you can see there are hardly any particles over here, only 0.002. That means only 0.2% of the size range of 5 millimeter that is there in the quartz, and probably 1.8% of size range between 5 to 6 will be there in the quartz. Rest has gone to the fines. And the higher percentage of particles in the size range of 8 and 10, they are in the quartz channel. So that's how the division has been done. So first 3 problems we have done. Now let us go to the next set of problems. Okay, now here in this problem we have to use the tabular data. So tabular data of particle size 5, 6 and 10 has been given. The grade efficiency of 1, 2, 97 have been given over here. So for that, we will go back to the Aspen Plus simulation window. In the classifier input, we will use the tabular data and we will choose particle size over here. So particle size has been chosen. The size curve tab is activated for us, and particle size in millimeter. So we give 5, 6 and 10, right? And there are 0.01, 0.02 and 0.97. These are the 3 things that has been said. Interpolation method by default is linear. Now, if you want to fit the best fit curve, then you can use the fitting. There are several options over here: Pleat, Rogers, Whiten and Moleras. You can use any one of them, okay? Or else you can just be happy with linear interpolation method. Probably do not need any other specification. You can just run it. Once you run, results are available. Go back to the stream result. Yeah, Here also you can find the separation is successful. Only 0.3% and here 1.2% are there within the size range 5 and 6.3. Most of the higher order particles are in the coarse range, so this is okay. We can accept this result. Okay, now go back to the problem statement and let us solve the Sifter models. Okay, there are 3 Sifter models. We have to pass some fluidizing gas into it first. So let us first pass a fluidizing gas of 170 kg per minute at 200 degrees centigrade 1 bar pressure containing 99.98 weight percent of air and 0.02 weight percent of water. Okay, so basically it's a moist air, and so let us use this information first. And it will be a gravity countercurrent Sifter model with cut size and density as before, and vapor stream pressure drop of 0.1 bar. So here the pressure drop information has to be given, and the pressure drop as mentioned over here, it is a constant pressure drop of 0.1 bar. So let us first go to the main flow sheet and let us add a material stream of gas, and we will rename it as air in, or say you can say air, and open air input. It is 170 kg, right? 170 kg per minute, 200 degree and 1 bar pressure, and mass fraction. So air is 0.998. So it is 99.98% of air and 0.0002, that is 0.02% of water rather. So that's how we fix the air information, and go back to classifier input where you have to use the Sifter model. And first let us use the gravity counter current, where you have to use cut size and cut density, right? So it is said the repeat the above by using gravity counter current Sifter model with cut size and cut density as before, and vapor stream pressure drop of 0.1 bar. So we have to use this information also. So vapor stream pressure drop is 0.1 bar. Okay. Now cut size and cut density, there is nothing about separation sharpness been mentioned. So let us use the same thing, and our problem is defined. So let us run. Let us see the Sifter model. Here you'll find the results are not that good because 17% of fine materials are there in the coarse channel. Okay, and 18% of 6.3 size group is there in the coarse channel. So this model is not functioning. These are considered to be fine materials. They should go over there, but it is remaining in the coarse material. Let us repeat the above using gravity cross current. So counter current is not helping. Let us see whether the cross current helps with a Sifter length of 3.5 meter and width of 1.5 meter. So with that, let us go back to classifier input and let us choose the cross current one, and length and width information you have to use. Length is 3.5 meter and 1.5 meter width. Run the process and check the simulation result. Okay, so this is somewhat good. You can see in the fines material, 84% of the fines material is there in the 5 millimeter range and 0.12% over here, and 10 millimeter is very small amount is there in the 10 millimeter range. Only 3% is in the 8 millimeter range. So this is somewhat good. So by using 3.5 meter by 1.5 meter shifter, we have achieved somewhat better result. Now let us use a wheel, impeller wheel, and check. So for that, the problem statement is repeat the above by using impeller wheel simple shifter model with separation efficiency of 90%. So separation efficiency information has been given. Impeller radius and height are given. It is 250 inches and 3 inches respectively. So for that, let us go back to the simulation window and use this information. Separation efficiency 90%, impeller radius and height 250 and 3 inches. Okay. So use impeller wheel simple with separation efficiency, radius and height. So separation efficiency is 0.9. Okay. And impeller wheel height is 3 inches. And radius is 250 inches. So just change the unit from meter to inch. Here also meter to inch. And run the simulation. And check the results. Well, the results are not that attractive yet. At least the cross current was working better than the impeller wheel or the counter current. Okay. So although the information that have been given in the problem statement, they are not the best set of information because they are collected from several journals and papers. But in order to have a better set of results, the best option is to perform some experimentation with proper classifier and then use those information into the model, find out the best fit and fit that information over here and run the simulation. I hope if you do in this manner, you will be able to run the classifier in a better way. Okay. With this, we come to the end of today's lecture. I hope you have enjoyed it and we'll come back with yet another interesting lecture soon. Thank you.